Okay, in this video I'm going to talk about the Pascal's formula about binomial coefficients. So the formula looks like this. So n minus 1 k plus n minus 1 k minus 1 is equal to nk. So all these are binomial coefficients, and just to remind like the definition of this binomial coefficient. So n k, this is equal by definition like n factorial over k factorial over n minus k factorial. And despite the fact that it's a fraction, it's always a natural number. It can be proven. So okay, so this is the identity that we need to prove. So let's prove this. So basically we just expand the binomial coefficients by definition on the left hand side. So we start with the left hand side and we expand both of them. So n minus 1 k plus n minus 1 k minus 1. So this is the definition, right? So we write it as n minus 1 factorial over k factorial n minus 1 minus k factorial. This is the first binomial coefficient, and the second one is n minus 1 factorial over k minus 1 factorial and n minus 1 minus we need to subtract from n minus 1 k minus 1, so let's write it this way. So n minus 1 minus k minus 1. Yeah. So so this is equal to so now we notice that we have the same factor in the numerator, right? So we can write it this way. So n minus 1 factorial, so multiplied by the sum of these two fractions, right? So 1 over k factorial n minus 1 minus k factorial plus 1 over k minus 1 factorial, and here we just simplify. So n minus 1 minus k minus 1, so basically minus 1 and minus 1, they cancel each other, right? So, and what remains is n minus k factorial. Okay, and so now we notice that what we have in the denominator is kind of like almost similar to like in this fraction and in this fraction, right? So we have here we have k factorial, and here we have k minus 1 factorial, right? So if we multiply in the second fraction, if we multiply both numerator and denominator by k, then we would have here the k factorial as well, right? Because k multiplied by k minus 1 factorial is equal to k factorial. So from this we can rewrite. So n minus 1 factorial multiplied by, so let's leave the first fraction for now. So in the second fraction we have, so we multiply both the numerator and denominator by k, right? So k over k factorial. Okay, let's write it more fully. So k multiplied by k minus 1 factorial multiplied by n minus k factorial. So we multiplied both numerator and denominator by k, and then because of this, right, we have that this is equal to k factorial. So now in the first fraction, what we have, so we also have here the second factor in the denominator is almost equal to this n minus k in the second fraction. So the idea is again to multiply both numerator and denominator by n minus k, and then this factor would turn into n minus k factorial. So k factorial multiplied by n minus 1 minus k factorial multiplied by n minus 1. And in the numerator as well, so n minus 1 n minus k n minus k. So now this product by the same rule, right, is equal to n minus k factorial. So now we have, in both fractions we have the same denominator, right? So we have n minus 1 factorial and these fractions, so this is the common fraction now. We have k factorial multiplied by n minus k factorial, and here we have the sum of the numerators, so we have n minus k plus k. So n minus k plus k, so minus k and k cancel each other, and so what remains is n in the numerator. So what we have is n minus 1 factorial multiplied by n, and in the denominator we have k factorial n minus k factorial, right? So now n multiplied by n minus 1 factorial by the same identity here, this is equal to n factorial. So this whole fraction is equal to n factorial divided by k factorial n minus k factorial. So, and this is by definition the binomial coefficient. This is exactly this definition, right? Yeah, so this basically concludes the proof. So we started with this sum of two binomial coefficients, and we arrived at this binomial coefficient, and this is exactly what we needed. This is exactly the identity that we needed to prove. So this concludes the proof.